Dear students, few days back I tried to contact with you through Skype, but due to poor connectivity, I was not able to contact with all the students. Then I received a large number of suggestions, and some of the suggestions were not acceptable, but I assured you that I will make some necessary arrangement to frustrate you. I would like to give some introduction about the fourth chapter because first three chapters we have already covered through various videos. The fourth unit is chemical kinetics. Kinetics means motion, but what does it mean in case of chemical processes? If the concentration of the reactants in the product will change with the passage of time, then we say the reaction is in motion or the chemical process takes place. And the chemical process means that the concentration reactant gradually decreases and the product gradually increases. The concentration is generally expressed in terms of molarity, that is moles per liter. Now this chapter deals with rate of reaction, life of reaction, half-life period of reactions, then order of reaction, molecularity of reaction, as well as the mechanism of reaction. The mechanism term we already studied in plus 1, that the case study of reaction involving all the intermediate steps, in it may be short-lived or long-lived, is said to be mechanism. Now, on the basis of time, the processes are divided into three categories, and first is slow reaction. Slow reaction means the processes which proceed at a very slow rate, that is, requires months, years, centuries, etc. Like rusting of iron, formation of coal, and formation of petroleum. A very large number of other processes are radio decay or some stable elements are also fall into these categories. It is very difficult to study to find the exact rate of reaction in case of slow reaction because the time is very large. Instantaneous, second is instantaneous or fast process. Instantaneous or fast process means the process which proceed within it, complete up within no time. That is requires less than 10⁻⁶ seconds. Like the reaction of sodium chloride with silver nitrate gives silver chloride. Process takes place in less than 10⁻⁶ seconds. And the normal watch cannot give the information about this. Only special techniques are used to study these type of reactions, like flash photolysis and laser techniques are used to study these reactions. Okay, we study about the moderate reactions, the process which proceeded moderate reaction means complete up in seconds or minutes or hours, like hydrolysis of ethyl acid or hydrolysis of sugar. They require around 3 to 4 hours for reaction, and we can easily study the laboratory about the rate of reaction. But what is the meaning of rate of reaction, or another term is instantaneous rate? Everybody knows that when the process proceeds, the concentration reactant decreases and the concentration product increases. If we burn the coal, the quantity of coal decreases and the quantity of CO2 increases. Now here I plot two graphs on the same graph paper. Here is a time. It may be minutes or seconds, it depends on the convenience. And this part is for reactant and this part is for product. And with the passage of time, the concentration of reactant decreases and ultimately may reduce to 0. And while the concentration of product increases with the passage of time, reaches to a certain value. Here, each and every interval is small. Interval like maybe interval of 5 seconds, 0 to 5, 5 to 10, 10 to 15, 16. The increase or decrease in concentration of reactant product is not uniform. It is exponential. If it comes out to be straight line, in that case it is very easier to define the rate of reaction instantaneously, the change in concentration of carbon dioxide. This is not the case. Like 0 to 5, 10, 15. Between 10 to 15 minutes, this much change in concentration. Now, this divided by this one means divided by 5, value is much larger than this one. During the same interval, this much small value changes. So here, the change in concentration per time is much smaller than this one. So we have to define the curve during which interval we are defining the rate of reaction during 5 to 10 or 10 to 15, 15 to 50, 20 to 30, in which interval. And that is why the rate of reaction or instantaneous rate is the change in concentration per unit time in a particular small interval of time d. Now dc is the small change in concentration, that interval is dt. And particular small interval may be 10 to 15, maybe 10 to 50, 15 to 20 or 20 to 30, whatever the case is. Now what will happen if I select the interval larger? During this large interval, the rate of reaction value changes so many times. And in that case, the change in concentration upon time comes out to be average rate. Or if I take total time, then it comes out delta C by T. In both cases, this is the average rate. But units remain same whether it is a rate of reaction or it is the average rate. Now, how to express the rate of reaction in terms of the concentration of reactants? Minus dc by dt. Negative sign is used. It is generally asked in the examination why negative sign is used to express the rate of reaction in terms of concentration reactant. Here, because the concentration reactant decreases with time, the change in concentration is C1, C2, the final C2. C2 is smaller than C1, as a result comes out to be negative, and hence the negative sign is used. On the other hand, in case of product, there is no negative sign because here the concentration C1 dash, C2 dash. C2 is much higher than C1 dash, and hence the net result comes out to be positive, and hence this one. What are the units? Units in general it's mole per liter per unit time. That depends on convenience of the reaction. It takes place in seconds, minutes, or hours, or years. So per year, per minute. So this is a general expression. With the observable per second, then it is per second. Or if the observed property is pressure, then it may be bar per unit time, millimeter per unit time, atmosphere per unit time. It is very understood. Per unit time is unity. When we use the term rate in each and every case, we use some unit. Unit is there. When we purchase some vegetables, we mention the item of the article in terms of per kg, then kg is the unit. When we purchase cloth, then the unit is meter, 100 rupees per meter, 150 rupees per meter. In the same way here, in case of rate of reaction, the unit is time. Maybe per second, maybe per minute, maybe per hour, maybe per year, and so on. Now let us take an example of decomposition of PCl5. How to express the rate of reaction in terms of the concentration of reactant. This comes out to minus dPCl5 by dt, because PCl5 is reactant and its concentration decreases with time. PCl5 is the molar concentration of PCl5. Outside is D, means the small change in concentration of PCl5 in a small interval of time dt. This is same as dPCl3 by dt, because the stoichiometric coefficient is the same and hence they are equal. But here is no positive sign. The rate at which PCl3 is formed, at the same rate CL3 is formed, because they are also in 1:1 stoichiometry. They have 1:1 stoichiometry and hence CL2 by dt. This is a very simple equation. Now, what will happen if it involves some coefficient during balancing, like formation of ammonia, and 2 plus 3 is 2, 2 is 3. Then rate of reaction is minus dN2 by dt. Minus dN2 means the small change in concentration of nitrogen in a small interval of time dt in an interval of time dt. If the interval is not, then here I will mention here delta, like this. Here outside the derivative is 1 by 3. Negative sign is due to reactant, its concentration decreases with time and the coefficient comes to the denominator. Same is the here, but here is no negative sign because it is a product. The rate of reaction sometimes is same as rate of appearance or disappearance. No doubt, in case of reactant the concentration decreases and hence the reactant disappears and product appears. And the rate of disappearance of nitrogen dN2 by dt, which is same as rate of reaction. During numerical, negative sign has no significance. This is only mentioned during the expressions. And in case of hydrogen, rate of disappearance of hydrogen, this one, not 1 by 3 is included. This is that. If I include 1 by 3, then it comes out to be a rate of reaction. And if I don't include the 1 by 3, then it is rate of disappearance of hydrogen. Similarly, here rate of disappearance of now ammonia is the product, rate of appearance of ammonia. dN is the T If the prefix is 1 by 2, then it is not rate of appearance, it is the rate of reaction. So we must have clear in mind there is a difference between rate of appearance and disappearance in comparison rate of reaction if there are some stoichiometric coefficients are involved. Now I would like to solve some numerical problems related to this topic. For example, in the formation of ammonia, the concentration of nitrogen decreases from 0.05 m to 0.025 m in 30 minutes. In the formation of ammonia, the concentration of nitrogen decreases from 0.05 m to 0.025 m in 30 minutes. Then, what is the rate of reaction? Rate of formation of hydrogen, rate of disappearance of hydrogen and rate of appearance of ammonia through this method. The reaction is same, then the rate of reaction since the interval is large, I will use delta NH3 and delta N2 delta T. Then the value is 0.005 minus 0.05 upon 30 or 0.025 upon 30, or this comes out to be 0.00833 or 8.33 into 10 to the minus 3 mole per liter per minute. Or you simplify it. You can simplify in this manner. 25 by 30 into 10 to the minus 3. Now, I have to write down the rate of disappearance of hydrogen. We know that d N2 by dt is equal to 1 by 3 dH2 by dt, or rate of disappearance of hydrogen equal to dH2 by dt is equal to 3 into d and 2 by dt. That is 3 into 8.33 into 10 minus 1. Similarly, rate of occurrence of ammonia di2 by dt is equal to 1 by 2 d minus 3, sorry, delta delta. In this way, we have to solve the numericals. The only basic difference is we will use the value delta if the interval is large, and in case the interval is small, then you will use the sign small t. This is the basic difference. Units per second in this case, otherwise the per minute, per years, per day. As mentioned, sometimes we also ask some question. This is the rate of variation expressed in terms of per second. Then here 30 into 60, and you will get the answer in terms of per second. That hardly matters. Now, what is law of mass action? We studied this one. The rate at which reactants get together is directly proportional to the rate at which reactant react together is directly proportional to molar concentration of reactant. Suppose A is an reactant and gives product. Then rate is directly proportional to concentration, molar concentration of A, or rate is equal to K into A. Where K is proportionality constant, later on we call it as rate constant. Similarly, A plus B gives product. Then rate is proportional to concentration of A and or rate is equal to K to A. Suppose A moles of A and B moles of B gives product. Then rate is proportional to A raised power A and B raised power B, or rate is equal to K into A raised power A and B raised power. Here K is rate constant or specific reaction rate or velocity constant. We discussed this topic in +1 also in its equilibrium chapter. How to define rate constant or specific reaction rate or velocity constant? If the concentration rate is taken as 1, then K is equal to rate of reaction. Rate constant is equal to rate of reaction. And also 1 and 1. 1 raised to 1, A, 2, 3, 1 raised to 2 also comes out to be 1. 1, 2, 3, 4 comes out. 1 multiplied by 1 comes out to 1. 1 multiplied by K comes out to K. And hence, rate constant or specific reaction rate or velocity constant is equal to rate of reaction when concentration of all the reactant is taken as unit. I repeat it again, rate constant or specific reaction rate or velocity constant is equal to the rate of reaction when concentration of all the reactant is taken as unit. Now, units of rate of reactions are constant for all the reactions, moles per liter per time. But what are the units of rate constant? Here we study. Suppose the rate is mole per liter per second. K and the concentration is expressed in terms of mole per liter. This mole liter cancelled out. We get K is equal to a second. Units of rate constant is per second. And in this case, mole per liter per second, mole per liter, mole per liter. Here K comes out to be per mole liter per second. If there is change in reaction, the units will also change. So units of rate constant is constant for a given reaction at a constant temperature. But units vary from reaction to reaction. Sometimes with a change in temperature, the reaction changes, and that case the units also changes. In case of rate of reaction, units remain same, while in case of rate constant, the units vary from reaction to reaction. That depends upon the type of reaction. If the type of reaction is similar, then the rate constant units are also similar. Now, after this, let us pick up the factors affecting the rate of reaction. There are various factors which are affecting the rate of reaction, like first, nature of reactors. A chemical process means in which old bonds are broken up and new bonds are formed. Like hydrogen plus chlorine gives HCl, and each there is a linkage between hydrogen and hydrogen, and the linkage between chlorine and chlorine. The linkage H and Cl will only be formed if there is a fission between chlorine and H and H. Only then the reaction is possible. And that is why I stated that a chemical process means in which old bonds are broken up and new bonds are formed. So the process in which the bond fission is very easy, proceed at a much faster rate than that of the processes in which the bond fission is not so easy. In your book, it is mentioned there is the reaction between NO and O2 changes to NO2, and this reaction is very fast. While this is relatively slow. Though they appear to be similar, then the rates are different. There is very low stability of NO in comparison to CO, and hence very less energy is needed for the reaction to take place, and hence this reaction proceeds at much faster rate than that of this one. But I will give you another example which you will perform in the practicals. The oxidation of ferrous sulfate is much faster than oxidation of oxalate ions using common oxidizing agent permanganate. In both cases, I will oxidize the ferrous sulfate solution with K1O. I will oxidize the oxalate with also K1O. But this reaction is much slower, even requires some heating. But in this case, not so. Why? Because in aqueous solution, it dissociates to Fe2 positive and SO4 negative. As it is an ionic compound, so the only time required for oxidation of Fe2 positive to Fe3 positive. But here, lot of energy is required for the fission of CC bond. Only then you will get CO2 and O2. and hence this reaction used to be stopped. In the today earlier explained, the ion reactions are very fast and the molecule reactions are little slow. Another part of the nature of reactant is surface area, but this factor is only applicable in case of heterogeneous reactions. Surface area. This fact is only applicable for heterogeneous reactions. There are two types of reactions, homogeneous and heterogeneous reactions. Homogeneous reaction in which all the components of the reaction mixture are in the same phase. Like this one, NO is gas, O2 gas, and hence this reaction is homogeneous reaction. CO plus O2, CO2, all in gaseous phase. Nitrogen, hydrogen, ammonia, all are in gaseous phase. They are homogeneous reaction. So in case homogeneous, this factor has no role to play. This factor is only applicable for heterogeneous reaction. Burning of coal, burning of petroleum. So C plus O2, CO2, C is in solid state and CO2 is in gaseous state. So in heterogeneous reaction, at least one component of the reactant exists in a different phase. Solubility of sugar in water. The sugar solid plus water liquid, sugar solution liquid. The sugar in solid state, hence the reaction is heterogeneous reaction. So in case of heterogeneous reaction, greater the surface area, faster the rate of reaction. But in case of solid, how will you increase the surface area? The only way is change the substance into small particles. Small particles. And if you convert in the form of powder, the surface area is much higher than that of the solid block. And due to this reason, a lump of coal or coal powder burns more violently than that of a block of coal. Wooden shells burns more violently than that of a wooden logger. Now in case of charcoal powder, if I say charcoal powder, I assume that it may have some maximum surface area, but it is not so. We can further increase the surface area of a charcoal powder by heating in a vacuum. Because if the charcoal is present in air, that will absorb some gases on its surface, and the surface where gases reservoir are not available for chemical reactions. But if I heat in a vacuum, all the absorbed gases will leave the charcoal, and hence the surface area is further increased, and such a charcoal is called as activated charcoal. Very simple method is to heat the charcoal in vacuum. You get a air-free, nitrogen-free charcoal, that is called activated charcoal. So there are two things which are considered in nature of reactant. Second is concentration of reactants. According to law of mass action, the rate at which reactant react together is directly proportional to molar concentration of reactant. Higher the concentration, faster will be the rate of reaction. And that is why coal powder burns more violently at the initial stage than that of later stage. In domestic purposes, initially the gas burns more violently, and after about 1 month the flame from the gas burn is little slow. Why so? The concentration of a gas decreases with the passage of time, and if the concentration decreases, the rate of reaction also decreases. Now, if I lit the candle in the open, that burns less violently than that of a if the candle is kept in an oxygen jar. Why? For combustion, it needs oxygen. Air contains only 21% by volume oxygen, and oxygen jar cylinder contains 100% oxygen, and hence it burns more violently. So this is the concentration of reactant. Then next factor is the effect of radiations. Effect of radiations. Effect of light, because of and this factor is only applicable for photochemical reactions, photochemical processes. The processes you proceed by absorbing light, like photosynthesis. Plants synthesize their food in the presence of sunlight, not in moonlight. Decomposition of silver bromide we did in 10th class, silver and bromine, and that concept is utilized in photography. Vision, that is also a photochemical reaction. So in case of photochemical reactions, greater the intensity of light, faster the rate of reaction, because most of the photochemical reaction proceed by absorbing light at certain frequency. But there are some processes which proceed by absorbing light at different frequencies. If it is so, in that case, higher the frequency, faster will the rate of reaction. If it takes place at variable frequency, get your increasing wavelength and decreasing frequency. Suppose the reaction takes place in the red region as well as the blue region. Since the blue region has high frequency, hence in this region the reaction will proceed much faster than that of it in a red region. And generally our demand is for a gas burner it should be bluish or greenish color, because in that higher the frequency, higher will be the energy which is provided to the cooking material. In case of red region, there is incomplete combustion, less heat is generated, and hence less heat goes to cooking material. Not only blackness the container, more cooking time is required. Next is temperature. For any reaction to proceed, they have to cross the energy barrier. The reaction may be exothermic, may be endothermic. It has been observed the rate of reaction is almost doubled on increasing the temperature by 10 degrees Celsius or by 10 Kelvin. Suppose this reaction is at 373 and this reaction at 383. For a same reaction, the ratio comes out to be approximately 2. Though the speed is not doubled, speed enhancement is approximately 0.1%, but the rate is doubled because the number of effective collisions per unit volume per second is almost doubled, and that I will explain in the later stages.